Okay, so thanks very much for the introduction, and yeah, thanks to Shimadzu for inviting Peak to participate in today's webinar. And yeah, so we'll be looking at hydrogen carrier conversion for gas chromatography applications, and I'll basically be talking you through a few aspects. First of all, looking at the helium shortage, because I'm sure for those of you who are attending today, this is probably one of the key reasons that you're interested in today's webinar. And we'll be looking at the alternative carrier gas options. I have a couple of examples of applications using hydrogen carrier gas for GC. And then I'll look at some options for gas generators that Peak offer, just to give you an overview if you're not too familiar with those products. So by way of a brief background into the current helium shortage, looking back a few years, back to 2018, around 85% of the world's supply came from Qatar and the US. Things have changed in the last few years, where the US has basically reduced availability of helium as they have wound down their storage facility. And so additional supply has been available from Russia, Algeria, other sources in the US, as well as other producers of natural gas, because helium is a byproduct of natural gas typically. There are also some new sources of helium that are being discovered, but they're not yet online. So along with some geopolitical events recently, and also some maintenance issues at some of the key supply plants, this has all kind of created a perfect storm where this has reduced overall supply of helium. And so what we're seeing regionally is that some regions still have supply, but prices are increasing significantly. Other regions have actually got extremely limited supply, and so suppliers have actually been rationing the helium to customers and limiting the amount of gas available. So when we look at the applications that use helium, the figure on the right just gives you an idea of the key applications using helium and a kind of overview of the main resources or supply areas of helium. You can see that cryogenics and welding are by far and away the largest consumers of helium. GC analysis, GCMS analysis would sit within the analysis balloon there. So an estimated 1% of global helium is used for GC and GCMS analysis. So obviously when it comes to supply and demand, the demand for GC and GCMS analysis is actually quite low compared to some other applications. And so suppliers have to prioritize depending on what the demand for helium is and what availability they have. And so there's really been a trickle-down effect that has impacted a number of labs worldwide. And so this has, as I mentioned, increased the cost to the labs, which has corresponded to an increased cost of analysis and higher operational costs for using helium. Can also, of course, impact on revenue if you're working in a contract lab, and of course can result in delays for research or analysis. So in addition to the difficulties in getting supply and also the corresponding price increases, there are other potential issues associated with using helium cylinders. So there's also some kind of hidden costs that we sometimes refer to. So these are things like the ordering process and an organization behind the scenes. And there are some safety or potential safety risks associated with using large cylinders of gas, including helium, as well as the risk of impurities when changing cylinders over. So in the face of depleting supplies and increasing costs, what choices do you have? So we recognize that not all GC methods can run using alternative carrier gases, but there are a number of options where this can be done, and we have a couple of examples later on. Your alternative to trying to adapt to the current situation is basically to absorb increased cost if you have supply, or deal with disrupted supply of gas and accept that this will maybe slow down your operations. And of course, this is not an option for everybody. So one of the key things that you can first of all look at is trying to conserve helium so that you have supply available for essential applications. So you can do things like carry out a helium audit where you look at your theoretical demand and then basically calculate what your actual demand is based on the number of cylinders that you are consuming. This would also involve doing things like checking for leaks in gas lines, making sure that you're using the gas saver option if available on your GC, and also looking at developing helium saving methods so that when GCs are not in use, they're not consuming so much gas. And so, as I said, really focusing on using helium for essential applications only. So when we look at the alternative options for GC, typically we're talking about nitrogen or hydrogen as the alternative carrier gas options. And when we specifically focus on hydrogen, typically we're talking about improved efficiency compared to helium and nitrogen. So the figure on the right is the Van Diemter plot, which I'm sure many of you have seen before. And what this illustrates is the efficiency of carrier gas across a range of linear velocities. And basically what we're looking for is that the curve is as low as possible, because this means that you have improved separation power within the column. So what we can see with nitrogen is that typically at low volumes, we have very good separation power with nitrogen, but as we begin to speed up, then we lose that separation power. So this would correspond to broadening peaks in the chromatogram. When we compare hydrogen to helium, we can see that as we speed up the linear velocity of the gas, we're not seeing this effect in terms of reduced efficiency of the carrier gas. So this means that hydrogen can be run faster than helium without sacrificing the chromatography or the quality of our chromatography. Now, it's not always the case, and of course one of the caveats to this is that hydrogen is a reactive gas, but when it is possible to use hydrogen, then it does offer us the opportunity for faster sample throughput. We also have benefits in GCMS ion source where it can reduce maintenance. And we have other potential benefits when using hydrogen where we have the potential for lower temperature separation, which means that we're not having to heat the GC oven to as high temperatures, which can correspond to longer column lifetime. So there can be a number of benefits to using hydrogen. And in addition to the fact that hydrogen is reactive and also is known to be a potentially explosive gas, you can also use a generator to generate it safely in the lab, so you're not having large volume storage in cylinders. So when we look at converting carrier gas, what are the key considerations? So one of the main things before you try to convert is to make sure that you educate yourself on the process of conversion, and that you're also aware of some of the potential difficulties that can be encountered, as well as looking at helium conservation as a first step. So back to a couple of slides, I talked about some of the things you can do. So checking the methods, looking for leaks in gas lines, etc., so that we're making sure that we're not wasting helium, and checking your actual consumption versus calculated consumption. The next point would be to check that your method can be run using an alternative carrier gas. So just remember that if you're using regulated methods, it may not be possible in some cases to use hydrogen as an alternative. And in other cases, you may need to demonstrate that you're getting equivalent chromatography results if you're using an alternative carrier gas. So that's a very important point before you start looking further into conversion of carrier gas. Then it's also a very good idea just to look at the overall effects on your method. So the Restec EasyGC method translator is a really useful tool that you can use, where you can basically input your current method parameters, and you can look at how the translated method will look. So that will calculate everything for you. And you can calculate based on things like whether you want to maintain the same efficiency in your system, or whether you want to speed up your analysis. So that it's quite a versatile tool, and definitely something that's worth looking at if you're not aware of that. In terms of reading about carrier gas conversion, there's now a lot of information available. I think if we look back 10 years, there's so much more information available to you. So if you look at things like the Restec blog, also Shimadzu website has a very good information about carrier gas conversion. And also on the Peak website, we also have application notes, of which I'll cover a couple of examples afterwards. It's also very important to check your manufacturer's guidelines for use of hydrogen, because there are some considerations, especially if you are using GCMS, and there are probably more considerations for GCMS, whereas for GC applications, it tends to be more straightforward to convert carrier gas. So in terms of the process of converting carrier gas, once we've checked that the method can be run using an alternative carrier gas, we need to review the current method information and check the instrument conditions. It's also a good idea to perform routine GC maintenance and carry out a full system check. The third point is very important. So if you're moving from helium cylinders to hydrogen generator, for example, it's very important to use new tubing rather than using the existing tubing. And this is because what can happen over time is that you can get impurities that build up on the inside of the tubing from the cylinder supply, and hydrogen will actually remove these impurities, or it will strip them away and will carry them to the GC. And so, of course, this can result in contamination of the inlet, or even worse, the column, and can result in increased background for some time. So it's definitely a very important point to change that tubing between your hydrogen supply and your GC. Then when you're looking at carrier gas, of course, you need a very high purity of gas. So typically for gas generators, you would be looking for 6 nines or better in terms of purity. So the Peak systems, for example, are 7 nines based on oxygen content. So that's really high grade, carrier grade hydrogen that you can use for carrier gas. So ensure that all of your connections to the GC are leak free, of course, because that can result in some contamination. And again, just to reiterate, follow guidelines from your instrument manufacturer or other reputable gas suppliers in terms of connecting in your new gas supply. And I have an example of this in a second, but when it comes to switching your method from helium to hydrogen, if possible, it's a very good idea to match the linear velocity of the new carrier gas to the linear velocity that you were using for helium, because this will mean that your peaks elute in the same order and will allow you to maintain the same overall program basically you'll just be changing your inlet pressure and possibly your split rate or split ratio if you're doing split injection. So this will make things easier, and then of course you can look to refine the method from there. So it's a good opportunity to optimize methods. Obviously, some of us will arrive in a laboratory and will pick up a method that has been developed previously, and will not always look to optimize. Changing carrier gas may offer you an opportunity to look at further optimization of your methods. So now we'll look at a couple of application examples. So the first one is fatty acid methyl ester analysis. So in this case, we were working with a customer who was struggling to get supply of helium for their carrier supply, so they decided to switch to hydrogen. And the conditions of the method you can see on the right hand side. And so basically the customer did try running the hydrogen faster at first, and then settled on matching the linear velocity. So I'll just go through some of the chromatograms from this study just to illustrate why. So as I'm sure you will know, FAMES is a very commonly used method. In this case, it was in food and beverage analysis. And we were looking at a 39 component standard mixture for the analysis here. And this was a GCFID method. So looking at the original helium method, had resolution of all 39 peaks, as you would expect. But there was one region that was less well resolved, which was of concern. And so this was where it wasn't sure whether using the potential faster characteristics of hydrogen would be an option. And so it was this region here, just past 40 minutes. And you can see around 43 minutes here, we have 5 peaks that are not very well resolved. And so this was an area of concern. So anyway, the customer carried out the conversion of carrier gas to hydrogen, and overall things looked okay at first glance. There was a slightly shorter runtime, but this region of the chromatogram did result in coelution of the peaks. So you can see here, peaks 29 to 33 were actually coeluting. So obviously this was not acceptable because we needed a full resolution of all the peaks. So made the decision to go back to the original linear velocity of carrier gas and basically match the hydrogen to the original helium method. And to achieve this, because hydrogen's more viscous, one effect that you may see, or you will typically see if you're using the same column dimensions, is that you require a lower head pressure on the inlet to achieve the same linear velocity. And so this was the case, and so there was a corresponding reduction of analyte transfer onto the column. So the customer adapted the split ratio and reduced the split flow to overcome this issue. So there was some optimization required, back to my previous point. And so in this case, the analysis time was matched to the original method. The first thing that was noticed was that the peaks became higher. So we were seeing slightly improved chromatography when using hydrogen. All 39 peaks were resolved, and looking at the region that had caused issues before, this was showing the same resolution as was found with helium, as you would expect. And so here you can see the results side by side. So you see the sharper peaks when using hydrogen due to better column efficiency. So this was definitely a good result. The analysis time was identical, meaning that all the peaks eluted in the same order, and basically meant that the customer was getting equivalent analysis without having the headache of worrying about whether they were able to get supply of helium. Okay, so now I'll just cover a second example. So this is a DHA analysis. Again, it's a GC-FID analysis. Now, this is an ASTM method. So this is, of course, a regulated method. And this was done in line with a revalidation of the method that has been approved for use with hydrogen carrier gas. So on the right-hand side, you have the conditions of the method. And so the DHA analysis is basically an analysis of PONA constituents, and as I just mentioned, had been revalidated for use with hydrogen carrier gas. So this is an approved method. So when using helium, typically run times using this method will be just over 2 hours. So it's quite a long method. So of course, in this case, there was interest in whether there was an opportunity to use the benefits of switching to hydrogen to increase the throughput of the sample without sacrificing any of the resolution, as we saw can occur in the previous example. So looking at the results, you can see that the top chromatogram is with helium carrier gas, the bottom chromatogram with hydrogen carrier gas, and really great result in terms of time, which represented a 40% time saving when using hydrogen carrier gas. But of course, again, need to make sure that all critical separations were achieved. One in particular that was of interest was looking at 1-methylcyclopentane and benzene, which are quite poorly resolved when using helium with the method. And as you can see in the middle of the chromatogram, you can see the larger benzene peak and 1-methylcyclopentane just eluting just before that. In fact, what we could see with hydrogen was that the resolution was actually improved despite running the sample at a faster rate. So this was definitely a very successful example of carrier conversion to hydrogen offering faster throughput. Now, of course, it's all very well being able to run faster, but another important thing is to make sure that the overall ratios of the key groups that were being analysed did not change and that there was no significant difference between constituents analysed. In fact, looking through the key constituents, there was no significant difference found. So this really demonstrated that the method works extremely well with hydrogen carrier gas. So you can get equivalent results in a faster time. So, of course, one of the things that you may be interested in when looking to convert to hydrogen is looking at what the potential cost savings may be for your laboratory, because of course investing in a gas generator, for example, is a capital investment. So I've got a little worked example here just to illustrate the kind of savings that you could expect to see. So if you are consuming 1 helium cylinder per month in your laboratory, this would equate to a quantity of gas equivalent to a 250 cc hydrogen generator running 24/7. So That gives you an idea of the kind of size of generator that you would need. So Peak has a 250cc model. So I've based this calculation on our own hydrogen trace generator. So based on this, you could expect to see an ROI in as little as 12 to 18 months. So I think that's pretty good, and hopefully you would agree with that. One of the benefits, of course, with changing to a generator is that the ongoing cost of ownership once you've invested in the generator itself is quite low. In terms of consumables on the system, so with Peak, we only have an annual change of the DI cartridge. So that's the deionizer cartridge that protects the cell. And you would need a source of deionized water and an electrical supply, of course. So based on the purchase of one of these generators, you could be looking to save around $30,000 over 5 years, including the cost of the generator. So that's certainly, I think, quite an attractive proposition. So if you think about the potential for faster throughput of analysis as well, if you're in a contract lab, you can actually generate more revenue through running faster. And on the other hand, you can save money through having a generator over the longer term. And it must be, I must add that if you maintain a generator, we would expect that you should see more than 5 years service from a generator. So in terms of the Peak generator solutions for carrier gas, we have our hydrogen trace generator. So I mentioned at the beginning of the presentation, the purity on this system is 7 nines based on the oxygen content. And so this is suitable for both carrier gas and flame gas for any flame detector. We offer 3 different flow rates ranging from 250 cc's up to 1.2 litres per minute. And if you needed higher capacity, we can actually connect multiple units together, so they can be linked using a cable, and they will basically work together to balance the operation of the generators versus the demand from your laboratory. In terms of the safety features on the Peak systems, we always carry out a safety check when the generator starts up to ensure that there are no leaks. We also have an extremely low volume of gas within the generator, and the generator also comes with a water loading pump, and we also have a deionizer cartridge as standard. We have an optional DI water bottle that is fairly inexpensive that can also be purchased with the generator if you need that. The generators are also stackable, so you can save space by stacking multiple units if you need to save space in the laboratory. And in the precision range, we also offer nitrogen and zero air options that can stack with the hydrogen generator. I mentioned the increased capacity via cascading. And in terms of maintenance on the hydrogen generator, it's extremely simple. It's just a change of the deionizer cartridge once every year, and this can be done by the lab team very easily in just a few minutes. And just a note on the, sorry, just skipped forward by accident there. Just a note on the certification that we have on our systems. We have full CE and CSA certification, which means they're extremely safe. We have to do a number of, demonstrate a number of safety features of the generator to pass CSA certification, and we are also Shimadzu QA approved. So we've been through tests with Shimadzu in Kyoto in Japan to ensure that Shimadzu approves the Peak generators. So in terms of maintenance, I mentioned the deionizer cartridge needing to be changed once every year. And we also have a 12-month comprehensive warranty on our hydrogen trace products. And in addition, we have a 36-month cell warranty. So this is on the condition that the correct grade of deionized water is used and that the deionizer cartridge is exchanged every 12 months. So very little for you to worry about once you have the generator installed and running. This slide just goes into a little bit more detail in terms of the safety features of the generator. So I mentioned that we're constantly monitoring the internal pressure. We also have external leak detection, so if there's a leak outside the generator, it will shut down after a certain time if it's basically supplying at maximum capacity, assuming that there's a leak outside. We also have a number of alarms, and the touch screen will also alert you if there's anything wrong. And in terms of certification, I covered the CE and CSA certification, and basically that ensures that we have no risk of a fire or explosion, even if there was a catastrophic leak of hydrogen within the generator. So as you will see, the Shimadzu GCs also are extremely safe when working with hydrogen, which will be demonstrated afterwards. So I would say it's a perfect partnership between the peak generator and Shimadzu GC. So covered the certification. Just a note on useful links and further reading before I finish my presentation. So the Peak website has information on our products. We also have application notes, such as the examples that I presented before. You can also get in contact with the team if you have any questions. And there's an email address. If you would like more information, you can email discover@peakscientific.com. And for any of the articles or application notes, they are available at that link there. So peakscientific.com/discover/articles. And of course, do look at the Shimadzu website. As I mentioned, there's a lot of good information available there, of course. There's a specific page on alternative carrier gas, which also includes some application notes. So that brings me to the end of my slides. So thanks for your attention.
Hello, everybody. I'm Naresh here, and my presentation basically including that how a Shimadzu Nexis GC is equipped with a hydrogen leak detection mechanism. What I'm going to include here is that Nexis GC-2030 product concept. Then what are the high-end features of Nexis 2030 GC is, and how a hydrogen carrier gas can be a safe option to replace helium. Now, coming to the product concept, Shimadzu Nexis 2030 GC is in pursuit of integrated control is a very high-end usability product, which has state-of-the-art user interface, simple and clear touch control, and very easy to maintain the product. It has very exceptional performance in terms of, we can say it's high-end performance. Then there are injectors, detectors like BID 2030 and very highly sensitive FID 2030 is equipped with this Nexis GC 2030. Whereas flow controllers and which are very excellent reproducibility they are producing. Now, high-end throughput, which is again a very important feature for any gas chromatograph product. Now we are building gas analyzers built specifically for your needs as per for gas and liquid applications, pressurized liquid gas applications. But optionally then a hydrogen sensor, which Dr. Ed has explained that how the hydrogen can be used as a carrier gas. Now to make it a safe operation, we must have a kind of a leak sensing mechanism. So what Shimadzu having that we are providing a hydrogen sensor, and so that you can safely use hydrogen as a carrier gas in your system. Now, when I come to the high-end usability, state-of-the-art user interface. You can say very touch panel where each GC coming with equipped with touch panel, as well as controls are very intuitive and clearly visible. You can see complete GC information on SPL, FID, temperature, flow controls, all can be displayed perfectly there. High-end usability, you can really improve GC control panel by using the Great Lab Solution software. And this Lab Solution software can work with the client server based options also, which is very easy to operate, and equipped with direct functionality. You can operate through your pad, and all those controls are easily available. Now, here's the point which we were explaining. A hydrogen carrier gas is a safe option. Now, this strong support for hydrogen carrier gas is there in the system. There are a lot of things has been explained by Dr. Ed, which suggest how to use, and the advantage of FAME analysis and the DHA analysis all has been explained. We could not find any much difference on it. And specifically, he informed that there is a good time saving available, and precisely my team has used these features, and by using even peak generator carrier gas, it's coming nicely. We're using those hydrogen gas generated by peak nitrogen hydrogen generator. So we could make the DH analysis perfectly. And impurities in benzene analysis, this is just an example we are showing. So a great amount of time saving is there. It's just a normal example. On the right side of the screen, you can see a hydrogen sensor, which is we're going to play a movie, which we made it for this webinar, and going to explain you how this hydrogen leak sensing mechanism is working in our system. And there is a, as well as beside this, the GC also has an automatic leak check function. So if you have, we use a hydrogen as a carrier gas, and or per se any carrier gas you're using, and you would like to see that system is leak proof or not. So if you use this option of the Nexis GC-2030, the system can check the automatic leak is there or not in the GC panel itself. Now, why we say a safe option? Now, in our system, in our GC, what the protection we have made, that if hydrogen leak is GCO 1.4%, then what the GC is taking action, that you have a temperature control off. So all temperatures in the GC panel or in the GC instrument are going to be off. The GC oven flap open to vent oven any air or leaked hydrogen, if it is there, going to be leaked out, as well as is displaying error message 51. Let's remember the point that the explosive option, if the 4% of hydrogen is there in an environment in the GC oven, then there is a possibility of explosion. But we are producing, the system is designed in a way that even if it is 0.4% leak in the total GC oven volume, which is 13.7 liter, well, we'll have this error message. Now, this is just an error message, but this is not something going to shut down the instrument. But what will happen if you have a high leak in the GC, which is close to 2%? The GC is going to take very strong action here, and that says the GC action shows GC shutdown. It will completely shut down the GC. All heater will be off, all flow control will be off, and a continuous audible alarm will be there. So that will surely help the operator to notice that, okay, this major leak has happened. Even if this is 2%, it is much safe than even explosion proof limit, which I already explained as a 4%. So within this 2%, you have this feature. And now we're going to play a short movie, which my colleague Sri will play to you to explain you that how this hydrogen leak sensor been installed in our Nexis GC-2030, and how this I will make a simulation that how the system is basically detecting this hydrogen leak in the system. Thank you very much.
Hello everybody. In this video, we are going to explain you that how Nexis GC-2030 is equipped with the hydrogen leak detection mechanism. The hydrogen leak detection tube, which basically is responsible for taking any leak in the GC oven, is installed in the GC oven. And this tube is basically connected to a hydrogen sensor. This hydrogen sensor is installed on the top of the GC panel, and this is the hydrogen sensor. And this hydrogen sensor is strategically mounted near the split injector. So if any leak is happening in the split injector or column broken, anything, that can be captured very promptly. The hydrogen leak sensor is basically connected with the two tubes, and these tubes are routed back to the pump at the rear side of the GC. You can see these tubes, as you can see, is connected with this pump, and this pump is operating in the cyclic mode, and every 15-second cycle operation is there. This pump is basically controlled by electronically through this PCB, and any signal from the sensor is directed to the CPU unit through these wires. This is the main GC screen by which we can access the all hardware configuration of the instrument. Now, specifically, if you're looking for any auto injector, you can click on this AOC tab. If looking for any detector or any specific injector, you can click on this tab. But if specifically you are looking for peripherals connected to hydrogen leak detection system, you can click this, and here you can find a different kind of interface connected. For example, if you have a CRG, which is liquid nitrogen or liquid CO2, you can access through this tab. Any auxiliary pressure control, auxiliary temperature control, or relay control, you can access through respective tab. But in general, if you're looking for specifically hydrogen leak check function, then you can come here, and then you see as the hydrogen sensor is installed, you can see it's usable. If you click it, you see the not applicable or usable. If it is not installed, it remain not applicable. So as it is already installed, so it remain as a usable part of the system. This is an example we are simulating here that how a hydrogen leak can be detected by the system. We have a column outlet which is giving us 5 ml of hydrogen continuously, and this error message is displayed because we have this oven door open. Now I'm putting this column outlet into the hydrogen sensor tube to simulate a continuous leak of a small minute leak of 5 ml in the total GC oven volume of 13.7 liter. Now I'm resetting this error message of oven door message, and now we should see that within 15-20 seconds we should have an error message displayed. At the same time, our temperature as well as the column flow should reduce. So here is the error message appearing, which says detector error 51, and it shows hydrogen detecting leak. Now you can see this message, as well as if you scan this message, then you can surely look into the remedy of how this error can be removed and what can be the possible cause of this problem. As this is a continuous leak, I am resetting now, and you can see this temperature and the flow start restoring it to the original value or the set values. Now basically it's a continuous process and it's restoring. So now I'm going to, as it is a continuous leak of hydrogen happening in the system, now we should have error message again appearing it, and again the flow and temperature should start reducing it. Now let's look for some time. Within 15-20 seconds, error message should appear again to us. Here it is. Again detected a leak, detected hydrogen leak, and the flow and the temperature start reducing it. So this is the way even a minute leak in the system can be seen. Here we are simulating how a big amount of hydrogen leak, what it will do with the system. So this is a 50 ml of hydrogen source. We have made it, and with this source coming out from a restricted tube, I'm going to put this restricted tube with 50 ml of hydrogen flow inside the GC oven. Right now, as there is no hydrogen leak, so the temperature of the ejector should restore as well as flow should restore. But I do expect that once the 15 ml of hydrogen leak, this is the temperature restoring. So once 50 ml hydrogen leak is there, it's a big amount of leak, then GC must shut down. So once this is done, and let's see how the GC is shutting down, and it should produce an audible alarm. Here's the GC shut down because of the leak detected, and a continuous audible alarm is now going to be heard by the operator present in the lab. So that's a very great protection.